probability, which will take the form of an extended lecture followed by a discussion. Our distinguished speaker, Professor Luigi Accardi from University of Roma Tor Vergata, is one of the pioneers of quantum probability. In the early 1970s, he joined the prestigious research team around Kolmogorov in Moscow within the framework of the collaboration between the Italian National Research Council and the Russian Academy of Science. Obtained his PhD at Lomonosov State University in 1974 with a thesis on non-commutative Markov theory under the supervision of Alexander Gelfand. Since then, he had held academic positions at several Italian universities and has been full professor at University of Roma Tor Vergata since 1980. He has visited leading research centers in many countries and has developed extensive scientific collaborations with colleagues in Italy, Russia, Japan, Tunisia, India, and the United States, and beyond. He has supervised and co-supervised numerous PhD theses in several countries, including my own, which is I regard as a great honor, and has served as editor and editor board member for several journals in probability analysis and mathematical physics. He's also co-founder of the Association of Quantum Probability and Infinite Dimensional Analysis and its QP conference series, which since 1998 has become a major form of the field, and this year held its 74th series. His work on extending classical probability notions such as conditional expectations and Markov chains and probability quantization paved the way into application in contemporary quantum science and technology. I now have the pleasure to invite Professor Luigi Accardi to deliver his lecture entitled Probabilistic Quantization in Applied Mathematics. Prof, please, the floor is yours.
The mic, please, Dr. Luigi. The mic. You are mute now.
Will you open the mic, Prof, please? Prof, if you
hello, can you hear me?
Yes, now we can hear you.
Very good. So I don't understand what happens because I press on the screen and I press share, but it doesn't.
Now we can see the screen. We can see the screen. And,
you can see,
you also.
But
yes.
Why I cannot? I don't understand. You can see or not?
Yes, we can see.
And why I cannot?
You can open the file directly, not on the Zoom, just the file you shared here.
Okay, let me see. How to do this? How to open directly?
You go to the PDF file that you shared.
Just some, huh?
Just from the PDF that you shared, from the icon you shared.
Just a moment. Let me see. It doesn't appear. Before it appeared. When I pressed before, it appeared, but now it doesn't.
Check for it, the PDF file. Your PDF file. Open it again.
But I cannot go into the, let me see. Let me try to, wait a moment. What I can do? Let me see again. It doesn't work.
maybe if you try to reshare again once, like
I can go out and try to share
yes.
again.
Yes.
If not, you minimize the session of Zoom and open your PDF file directly.
Okay, so what shall I do to go out? I don't understand. Maybe you ask me interrupt. Okay. And now I try again. Okay, now I see. Now I can see the screen. Okay. Can I begin?
Yes.
Yes.
It's okay.
Okay. So, first of all, I want to thank the organizer for this invitation, which turned out to be an occasion for me to speak with very old friends from many different parts of the world. And I want to thank not only the organizer, but also the participants who are here for this talk. So I want to discuss a question which is very simple to pose and to ask, namely, where quantization comes from. So probably most of you know that 2025 was declared the year of quantum because it was the centenary of the famous 1925 Heisenberg article where the mathematical formalism of quantization was introduced. So the basic innovation of this new mathematical formalism is expressed by Heisenberg commutation relation. Here on the left, there is the commutator between Q and P, and on the right, there is a constant, which is the famous Planck constant, which is strictly greater than zero. Now, Heisenberg did not deduce this formula. If you read this article, which is really a masterpiece, you really understand how art and science mix together in this paper. Really, he goes with intuition. So he did not deduce this formula. And he was very well aware of this. And he insisted that the only thing that we can say is that this formula works admirably to explain experimental data, and that the only thing that we can do is to utilize this formalism even if we do not understand where it comes from. He insisted on this point in many popularization books and in many popularization articles. And this was essentially the point of view of physics for about 100 years. We have a very beautiful mathematical formalism. Let us use it and don't worry about from where does it come. So the goal of my talk is to explain how a non-trivial generalization of a Heisenberg formula, but not only of this, of the whole formalism of quantum theory, naturally emerges from the combination of classical probability with the theory of orthogonal polynomials. There is only one thing mathematics cannot do, the single out the Planck constant, because we will deduce a generalization of this formula, but in our generalization, this constant will play the role of the variance of a Gaussian. And so it can be arbitrary. But in the Planck case, it has a physical meaning, is a universal physical constant, one of the most important. So the plan of my talk is this. I want to illustrate the main idea of probabilistic quantization in the simplest possible case. As you will see, this is the case of a single real valued random variable. Then, after having illustrated the main idea, that will be the main part of my talk. Then I want to mention some of the many research lines in pure and applied directions that arise from this basic idea. And the third part, I want to mention that, you see, this basic idea in the development of quantum probability was born rather late, in the end of the 90s. But before, quantum probability had a lot of interesting and important realization. I don't want to describe all of them, but I want to mention in case somebody is interested and want to make some question or have some more information. So let me start for the first part of the talk, and let me try to explain why we speak of probabilistic quantization. We speak of probabilistic quantization because we start with a classical real-valued random variable. For me, real-valued random variable means a random variable with all moments, with moments of all orders. So it means that any power of the random variable is in L2 and the real valued. So once we have this, we can form the complex polynomial algebras in the random variable. So these are the complex, you take a polynomial with complex coefficient and you compose it with a polynomial function, more precisely, because I consider polynomials as functions from R to complex numbers. So they are polynomial functions. This polynomial algebra is a star algebra for pointwise addition, pointwise complex conjugation, and it has an identity which is the constant function equal to 1. So if we define the we denote Px, the probability distribution of the classical random variable, we have a natural scalar product, which is the scalar product of L2 of R with respect to the probability distribution of the random variable. So this is the formula for the scalar product. So once we have the scalar product, we can orthogonalize the monomials. And here is the bridge with the orthogonal polynomial. Using the L2 scalar product with respect to the distribution of the random variable, we orthogonalize the monomial. And we obtain a sequence of, we don't normalize, only orthogonalize. So we want to have the coefficient of the highest degree to be 1. And this means that we are dealing with monic polynomial. Moreover, we will consider x, the random variable x, as a natural axiom, since on the L2 over P, just by multiplication, any element, since x is real valued, I can multiply pointwise any element of L2 of R by x. So, and I will denote phi0, the constant function equal to 1 when it is considered as a vector. When it is considered as the identity of the polynomial algebra, we use the notation 1. But when it is a vector, we use phi0, and to anticipate connection with quantum theory, we call it the vacuum vector. Now we call again, in order not to use heavy notation of the cyclic representation, we simply write P times a polynomial times the vacuum to say that we are considering the polynomial as a vector, not as a multiplication operator in L2 of P. Now 150 years ago, Jacobi proved the following relation called the Jacobi three-diagonal relation. That is, if I multiply the nth monic polynomial by x, I obtain on the right-hand side a sum of only 3 terms. A priori, it could have component on all monic polynomial, which is an orthonormal basis. The discovery of Jacobi is that x phi n has components only on n, phi n itself, the next orthogonal polynomial, and the previous one. The monic appears here in the asymmetry between, you see, fn plus 1 and fn minus 1, because this allows to introduce the original, what Jacobi called the principal Jacobi sequence, which is called omega n, and the secondary Jacobi sequence, which is alpha n. So, since phi n is an orthonormal basis, I will be a little bit a cavalier in the, say, orthonormal basis of what, but there are technical problems. But roughly speaking, in many important cases, an orthonormal basis of L2, of the L2 space. So we define three operators. We can define, because they are orthonormal, so we can define arbitrarily a linear operator on this basis. And this three linear operator act as the right shift in the monic basis, monic polynomial basis, as a multiple of as a self-adjoint operator with eigenvalues omega n, but no, this is A. Annihilator is left shift, and n minus 1. When n is 0, this phi minus 1 is understood to be 0. And alpha 0 is a self-adjoint operator with eigenvalues, Hermitian operator with eigenvalues alpha n. So, using this three operator, we write the Jacobi relation that you see upstairs here, the Jacobi relation, we say x phi n, which is a pointwise relation, we write as a vector relation. But since the phi n are an orthogonal basis, and this is true for every n, from the vector relation, we deduce an operator identity. And so we have that x is the sum of three operators. A daga. As you see, these three operators are very similar to creator, annihilator, and preservator, and this justifies their name. The non-trivial point is that the random variable x is the sum of these three operators. So classical probability considers random variable as atomic objects. But from the quantum point of view, we understand now that these are not an atomic object. Random variable have a finer structure, a microscopic structure, which is intrinsically non-commutative, let us say. But non-commutative is synonym, is a very special kind of non-commutativity, we will see. So it's not only generic non-commutativity, it is quantum. And I will try to explain in what sense is quantum and not generically non-commutative. Okay, so the three operators will be called the CAP operator: creation, annihilation, preservation. Well, I want to warn that there are many quantum decomposition. Now we know that there are many quantum decomposition. We can realize many quantum decomposition of the random variable. However, this one that we obtain from orthogonal polynomial is unique up to canonical isomorphism, that is intertwining the CAP operator. So the canonical, there are many quantum representations, but the canonical one is unique. So we have a probabilistic analog of what in quantum theory is called wave-particle aspect, because we have also wave-particle aspect of classical random variable. So you see, we will, if we promote, as it is possible to do, and at the end of my talk I will mention this, the analysis, if the conclusion we extend from single random variable to random processes, we recognize that the A plus A daga correspond to the diffusion part and the A0 to the jump part. And so the wave-particle duality again has appeared as a kind of universal probabilistic manifestation, not as a mysterious object related only to physics. It is a universal phenomenon of classical probability. Now, since we have the orthogonal polynomial, we have the orthogonal gradation, which means that since we are dealing with a single random variable, the space of orthogonal polynomial of degree n is simply the multiples of the monic orthogonal polynomial of degree n. Okay, now one can prove the important theorem that A annihilates the vacuum. Remember, the vacuum is the constant function equal to 1 and that the adjoint of the creator is the annihilator. The adjoint is for the L2 scalar product, and is understand all what I say is true on the domain of the orthogonal polynomial considered as vectors. So this is an invariant domain for all these cap operators. So what we say is algebraically true. Okay, they map this domain into itself. Okay, so this property, which is called the Fock property, is very important, and that is why phi0 is called the vacuum vector, is annihilated by the annihilator. Now, what we have, that by definition of creator, we have that A daga phi n is equal to phi n plus 1, okay? And we can write therefore the orthogonal gradation as, instead of writing phi n, we write A daga n phi 0, because since A daga is n plus 1, if I apply A daga n times to the vacuum, from what I see on the left-hand side, you obtain a daga n. So the orthogonal gradation is a natural quantum interpretation. And in physics, when you write the monic polynomial in this form, we follow the analogy with physics, because in physics, this object is called n-particle vector. And we have the same for a random variable, so we call it also the n-particle vector of the random variable, okay? So also any classical random variable, even if it is continuous values, it has discrete aspect, which is given by the n-particle vectors. Now, well, this is, I want to jump because it has to do with multidimension. What I want to come instead is this. Now, we have the three, I recall the definition of algebraic probability space. Algebraic probability space is a pair given by a star algebra and with identity. Star algebra for me always means with identity, unless I specify the contrary. So, and a state on this star algebra. The algebraic probability space is called classical if A is commutative, and the standard example, for example, is L infinity R with the Gaussian. This is in this case, the star algebra is in fact a von Neumann algebra. And a quantum probability space is the algebraic non-commutative. And well, I add typical is a B of H with the typical trace on typical state of B of H, standard example. So what we did, we started from the classical probability space. P is the algebra of polynomial algebra, so it's commutative. And the state is the expectation value for the distribution of X. But we have the quantum decomposition, and as we will see, the three operators do not commute. So the algebraic span of this three operator is a non-commutative star algebra, and this means that and moreover, that we have seen that the vacuum, we introduce the vacuum state, which is the expectation value with respect to the vacuum vector, and is essentially by definition the vacuum state, when restricted to the polynomial algebra, is identical to the expectation value with respect to the probability distribution of X. So what does it mean? It means that the quantum state on the quantum algebra non-commutative P is an extension of the usual classical expectation value. It's a natural quantum extension, because now I can put Z, any operator which has Z in its own, which has phi0 in its domain. I don't need that it is just a polynomial. in the x variable, okay? And so, again, we have, let me recall you again this gradation because it's very important. And this justify in any gradation, very particular roles are played by the gradation preserving operators, okay? Now we are in the very special case in which the gradation is one-dimensional. So if I preserve the space Pn is just the multiples of the n monic or orthogonal polynomial. So to preserve the space means that it is an eigenvector, okay? To this gradation preserving operator means that they are such that each phi n is an eigenvalue and there will exist a corresponding eigenvector. This eigenvector is this is very special for one-dimensional gradation. These eigenvectors are all functions of a special operator. All gradation preserving operator are function of a very special operator, which in physics is called the number operator, and which essentially in the physical language counts the number of particles of the nth sector, and in mathematical language, eigenvalue of phi n is the degree of the monic polynomial phi n. Now, so we see that any operator is gradation preserving if and only if there exists a function from n to the complex numbers such that this operator is a function of the number operator, and precisely the function which corresponds to the eigenvalues of A. Now, from this we have the fundamental result of the theory. This is the fundamental result. Namely, we have much more than the commutation relation. We have the multiplication table. Because you see, if A daga is the right shift and A is the weighted left shift, then by taking A and A daga, I first shift and then I go back. So 1 appears, omega n plus 1, because I have shifted. But if I do, and so if I use the operator notation that we have used for any gradation preserving, because of course this operator A daga is gradation preserving, because I first increase by 1 the degree and then I decrease by 1, so it's gradation preserving. So the same thing is true for A daga A, only that the order, I first decrease by 1 and then I increase. And so what I have is omega lambda. Remember, by definition, omega 0 is equal to 0 for us. Okay? So now, if we subtract the two identities that we obtain the commutation relation. But we could also add them, and we would obtain a Jordan algebra instead of Lie algebra. So that is what I say. The multiplication table is much more than the commutation relation. However, the commutation relation are there. So it means that A daga is now not a number as in Heisenberg case, but it is an operator, but a very special operator. It must be gradation preserving because it's the difference of two gradation preserving operator. And so it is a function of the number operator because the gradation has dimension 1, each term of the gradation. And we use this symbol to denote the finite difference operator omega lambda plus 1 minus omega n. So this is partial omega lambda, okay? Well, this is for those who know something of quantum probability is a comment that all the known deformation of Heisenberg, of the Heisenberg commutation relation, Fermi, Q deformed, many more, are particular case of this generalized. So, however, the difference is this. Now we deduce this formula, but the Q deformation are put by hand, artificially. No deduction, okay? So And so, since we have the commutation relation, like this generalized commutation relation, in terms of the Jacobi principal Jacobi sequence, it's very natural to ask: is there is there a classical random variable whose canonically associated commutation relation, which are this one, are precisely the Heisenberg commutation relation? Well, the theorem answering this question is the following. If for a strictly positive real number, sigma, the standard Gaussian measure with mean zero and covariance sigma is the unique symmetric probability measure whose commutation relations are sigma times the identity operator. So you see, we find a generalization of Heisenberg commutation relation. This is the only proof I will give in my talk, because the proof is extremely simple, but the result is important and justifies the name probabilistic quantization. So we have that this commutator is equal to this, but we want it to be constant because Heisenberg H bar is constant. There exists a unique random variable such that the secondary Jacobi sequence is equal to the integer and it has mean zero. Then this is and it is symmetric. And this is the Gaussian. So the phi-n are the Hermite polynomial. This is the proof, as you see. Extremely simple, but the result is non-trivial. So, okay, this is a comment. Let us skip because of time. I am very short of time. So now there is an issue. We have in physics, you very frequently find the expression A daga plus A, and they are called field operator in infinite dimension or finite dimensional field operator, position operator in the finite dimensions. Okay. Now we want to understand the meaning of the preservator, because the preservator in physics is not considered as kinematics, it's considered as dynamics, for reasons that I cannot explain now for reason of time. Now let us recall the following definition. A classical random variable, real valued, is called moment symmetric if the odd moment vanish. For example, the Gaussian is symmetric. Standard Gaussian means zero because odd moments all vanish. The following theorem explains the probabilistic meaning of the preservation operator. A classical random variable is symmetric, moment symmetric, if and only if the annihilation is identically zero. Okay? So as I said, in physics, you have, this is called the position operator, quantum fields in infinite dimension. But what does it mean? It means that when you only consider this and you don't consider the full quantum decomposition, you are limiting the physics to those random variables whose vacuum distribution is symmetric. Okay? So this is a very strong limitation, and this has important consequences. But let us now speak of another important remark, because as you remember, Heisenberg did not formulate the commutation relation in terms of A and A daga, like we have in this theorem. You see, in this theorem, we have the commutation relation in terms of A and A daga. But if you remember, in Heisenberg case, they were expressed in terms of position and momentum. Now, in classical probability, we have already seen that the role of position is played by the classical random variable x. So what is momentum in quantum probability? Well, this turns out to be a rather subtle question. But we want momentum to be an observable. We want momentum to be a self-adjoint operator. Now, we in usual boson also Fermi quantum mechanics, momentum is defined as I times the difference. So position is the sum for a symmetric random variable. You see, here I have emphasized that the random variable must be symmetric. For a symmetric random variable, we in physics you define momentum in this way. I mean, for boson random variable, you define momentum in this way. So we generalize the physicist's definition. Okay? Unfortunately, this generalization works only if the random variable is symmetric. Otherwise, you can define, of course, but you will not have an Hermitian operator. And momentum must be Hermitian if we want it to be an observable, okay, in the quantum case. So why this is the natural definition of momentum? Well, because since P is a linear combination of A and A dagger, Q is a linear combination of A dagger, and we have the commutator of A and A dagger, automatically we have the commutator of P or Q. And therefore we compute this commutator and we find that it is twice the same difference, omega n, omega lambda plus 1 minus omega n, this partial de lambda, remember. So we know that in the Gaussian case is constant. If we choose the constant equal to 1/2, this is due to the normalization, then we find the Heisenberg commutation relation as originally formulated by Heisenberg. So also the original formulation is deduced from probabilistic quantization. You see? But now we have a much more general formulation of Heisenberg relation. And this is true for any symmetric random variable. So I want to anticipate one of the open problems that I want to discuss. There will be many technical open problems, but there are some important conceptual open problem. And this is a conceptual open problem. So if in the Heisenberg case, we know that every position operator is canonically associated to a momentum operator. And momentum has a very clear interpretation. For example, in group language, it is the generator of the translation in the position for the functions of the position. Okay? What is the interpretation of momentum in classical probability? So we know that now that classical probability, any classical random variable, is associated with the momentum. But momentum is also act and leaves the polynomial algebra into itself, because A and A dagger leave the polynomial algebra onto itself. So it has finite expectation value for all orthogonal polynomials. So it is a random variable, a classical random variable according to quantum probability. Every self-adjoint operator, let us say Hermitian operator in the moment case, is a classical random variable. So P of x is a classical random variable, and it is canonically associated to the classical random variable x. How to interpret it? For example, suppose x is the price of a stock option. What is P of x? How to interpret P of x? You see, this is a problem that does not require a skillful technique, but it requires some insight in what we are describing. You see, physicists had this insight in quantum theory, but quantum theory took 100 years to develop. Now we want to develop this kind of insight for classical probability. This is a conceptual task which I consider relevant. You see, And I invite young, especially, but everybody to reflect on this purely interpretational problem, okay? Okay, and this is the problem that I discussed, the interpretation. What is the conjugate moment? What are the meaning? What is the probabilistic interpretation of the conjugate momentum of an arbitrary classical random variable? Okay, now with this example, I think I have expressed the main idea that I wanted to convey to you. And you see, I have explained this in the simplest context, the simplest framework, which is a single real-valued random variable. But even in this framework, which is very, very simple, you see, I hope we will have time to discuss a little bit the multidimensional case. And everything changed radically except in one case. And this one case is the only case that has been considered in the whole physical literature. So the only case is in some sense, what probabilistically is considered trivial one, simple, the simplest one. So let me make a very partial and incomplete list of what we could discuss. Well, remaining in the framework of a single random variable. So in the framework of a single random variable, you can ask, okay, we know that in the standard boson theory, the momentum associated to the standard Gaussian random variable is the generator of translation, which means I times the derivation, the derivative operator. So you can ask, what is the momentum in the case of random variables, classical random variable, which are not the Gaussian? Okay, we have begun to study this problem starting from the simplest probability measure. Again, what does it mean simplest? This also can be explained quantitatively by probabilistic quantization. Probabilistic quantization can attribute a numerical, an index which is made by a pairs of numbers, including plus infinity, which in some sense classifies the complexity of the measure, or the classical measure. So in this hierarchy, the simplest class of probability measure is what we call the semicircle arc sign class. And the semicircle arc sign contains infinitely many measures, classes of measures, which are not, we generalize the semicircle and the arc sign. They belong all to the same complexity class, which I will not have time to describe. And so in this sense, to speak of the simplest is not a kind of intuitive connotation. It's a very precise quantitative mathematical definition. So we compute the simplest measure in absolute, which is non-trivial, which means not a convex combination of delta measure. Simplest measure is the semicircle. From the Jacobi point of view, why this is the simplest? Because it's symmetric. So alpha n is identical, secondary Jacobi sequence is identically equal to 0. And omega n is constant. Is a strictly positive constant. Okay, so it's the simplest from the Jacobi point of view. But you see, so we studied with Tarek Hamdi, which is very good expert in harmonic analysis. We studied the simplest possible case. What is momentum? The answer is non-trivial. The momentum operator associated to the arc sign random variable is the Hilbert transform with respect to the semicircle law. So the analog formula of the standard a Hilbert transform in terms of principal value integral, but the integrating measure is not like in Hilbert transform, the Lebesgue measure, but the semicircle measure. This is not a kind of exotic object. Okay. I did not mention here, but let me say, if you want, I can mention two very interesting, special, very applied fields in which the semicircle Hilbert transform is widely used. So semicircle Hilbert transform arises naturally in quantum probability, but it has a long history, not in pure mathematics, but in applied mathematics, in aeronautics and in pattern recognition. Okay, I anticipate. Now, second question, the second simple. So the semicircle is the simplest. It's the simplest from the Jacobi point of view, because the principal Jacobi sequence is constant and non-zero. The semicircle belongs to the same class in what sense? The omega n is not constant, but is constant starting from n equal 2. So omega 1 is the variance. Omega 2 is a very interesting probabilistic interpretation. So in this sense, the semicircle is the next step after. So it's constant, and you can understand how the other classes will be formed. So the other class, we generalized the semicircle, is formed by considering a omega n sequence, omega 1, omega up to a certain number, k, and then constant from k plus 1, from k on. These are all beautiful classes of measures, non-trivial. The explicit form of the density is known for a k equal 3. Already for k equal 4, I think a good harmonic analyst should be able to find the explicit formula for k equal, at least for k equal 4, because the continuous fraction is very easy to compute in this case, and therefore you can apply the Stieltjes inversion formula to deduce the density. So conceptual is not a difficult problem. However, you must be able to do this, okay? And so this, in the case of the arc sign, the similarity of the two is shown by the momentum similarity. So in the semicircle case, momentum is in the semicircle case, the momentum is just the Hilbert transform with respect to the semicircle law. In the arc sign case, it is the same Hilbert transform, semicircle Hilbert transform, plus a rank 1 operator, which is uniquely expressed in terms of the Chebyshev polynomials, which are the monic polynomial of the arc sign. So, this is very interesting. If somebody, maybe on this, I would like to say some additional word. But first, I want to do the list of possible topics. Then I will do something more to explain this idea of Gaussianization is very natural, and in my opinion, another distinctive aspect of probabilistic quantization that is worth to go through, to look through. Okay, so at the moment I don't discuss, but I want to complete my list. When I've completed my list, I will discuss at least this argument in a little bit more detail, okay? Because this argument, this is related to many other important problems of probabilistic quantization. Okay, now my list now, as I said, there are a lot of other things in the one-dimensional case. For example, coherent vector, exponential vectors, which are very famous in quantum. They have a very nice analog here, but they not always exist. Depends on omega n when they exist. And they have very nice, for example, in the semicircle and dark sign, we can compute them very explicitly, and very nice property they have. Then, the Heisenberg indeterminacy principle. Now we have Heisenberg indeterminacy principle for every classical random variable. All these things are in the one-dimensional list, but I have not listed them explicitly. But there are many others. Let me now go to the most difficult part, which is the object of our research, namely the multidimensional case. The multidimensional case is hard because even the simplest nonlinear, because essentially it has to do with nonlinearity. We know that even the simplest nonlinearity, the quadratic case, in the quadratic case, we have the solution. We know what it is, the space, and it is very interesting, but I have no time to discuss. But quadratic quantization is well understood in 1 degree of freedom. It is not well understood yet in a number of degree of freedom greater or equal than 2. Of course, formally you can define and you can say a lot of mathematical things. But to give a theory on which you can do really explicit calculation, we are not yet at this point. So, but there are a lot of formulas that are interesting, that they exist. So let me I want to mention of the multidimensional case only one conceptual new point, which appeared in probabilistic quantization and was not known in usual quantization, namely the emergence when the random variable is a vector-valued random variable with values in a real vector space of dimension greater or equal than 2, new phenomena appear. A new type of commutation relation appear. If you remember, I gave the proof of the commutation relation and the multiplication table in the one-dimensional case, because in the one-dimensional case, everything is very simple. But nevertheless, when you do the calculation, it's non-trivial. But in that case, you have only one commutation relation, and they come from the fact that A daga and A daga A are gradation preserving operator. This property is preserved in the multidimensional case, and this gives rise to a commutation, a natural generalization of the usual quantum commutation relation, of Heisenberg commutation relation. By the way, also in the multidimensional case, the Gaussian is the unique symmetric case, a probability measure, and whose commutation relation reduced to the multidimensional Heisenberg one. So also in this case, the characterization theorem is extended. But what I consider very important is that starting from dimension degree of freedom equal to greater or equal than 2, a new type of commutation relation appear. And this new type of commutation relation were never considered in physics. And we know why. And this is to do with the quantum characterization of product measures. And so these topics are very interesting. And they still concern the probabilistic quantization. So up to now, I have spoken of the possible line of research that come out from probabilistic quantization. However, probabilistic quantization was born about 25 years ago, or a little bit more. And before, there were other 25, because quantum probability now begins to be a rather old discipline. So in the previous 25 years, a lot of interesting results were obtained in very many different directions. These results now are beginning to find wide applications in many fields, not only in physics, but in engineering, in control theory, in communication theory, in reliability theory, in machine learning, in numerical analysis, both applied to physics and standard one. Okay, and these applications are increasing exponentially with the passing of the time. So let me mention what were the line of research which were developed before probabilistic quantization, so let us say up to 2000, to the year 2000. Well, in chronological order, the quantum Markov chain, and more recently, this is the very recent of the 2020, the development of hidden quantum Markov processes. This is a topic that deserves, again, it is completely new, because in physics, they had the analog of the Gaussian states, and they were called the quasi-free state in physics, but they had no analog of Markov chains. So this is an important object in physics, in quantum information, in any application of, and now with the bridge between classical and quantum probability, we know that in any probabilistic theory, quantum Markov chain will be important. By the way, quantum Markov chain also produce very nice explicit example of non-Markovian Markov processes, namely processes with memory. So even from the classical point of view, quantum Markov chains are very interesting. If somebody wants, I can say just a very few words, because as you understand, the field had a huge development. Then there is what is for me, in order to describe quantum Markov chain, you need to describe Markov property. And the Markov property, to define Markov property, you need conditioning. So what is quantum conditioning? Well, quantum conditioning is very fundamental. Why? Because it is the only part of probability theory in which the obvious translation, commutative, non-commutative, does not work. Every other part of probability theory has a very easy translation in the non-commutative language. Conditioning is not. And there are physical reasons for this. So quantum conditioning is another fundamental topic. Then the very special case of conditioning. Conditioning is a quantitative measure of dependence of random variable. So the extreme case of conditioning is independence. So independence has also had a huge development, and now with probabilistic quantization, we have a good understanding of what these uncountably notions of stochastic independence mean, probabilistically, in the sense of classical probability. We can discuss this, probably there will not be time. So let me anticipate that what were called probabilistic quantization has made clear that what in the past we were calling stochastic independencies are in fact dependencies. They are what in classical probability, a generalization of what in classical probability we call coupling. A coupling means if you have two probability, an example of coupling is this. You have two probability measures on the real line, and you want to consider all the probability measure of the patients on the product of two real lines, such that the marginals are the given one. This problem is a very widely studied problem in classical probability, and also in quantum now has begin to be studied. I well, but the crucial point is that we understand, for example, that Fermi quantization is probabilistic quantization plus an algebraic constraint. In classical probability, we are accustomed to put probabilistic constraint. So very, very much is used stop times to create couplings. But in quantum probability, we have a much more freedom because we can put algebraic constraints. And the transition from boson quantization is just pure orthogonal polynomial theory. Fermi quantization, and the boson quantization correspond to Gaussian. Fermi quantization correspond to Bernoulli plus Pauli exclusion principle. Pauli exclusion principle in mathematics, you can formulate it as an algebraic constraint. This algebraic constraint uniquely determines the probability, and this is Fermi quantization. So and this is true for all other independencies. They are all hidden dependencies. As my friend Romuald Lenczewski was the first to have the intuition of this. He first said that algebraic stochastic independencies are in fact hidden dependencies. And I immediately found this remark very deep. Okay. Then I will absolutely have no time to discuss one of the most important branches of quantum probability from which all this development were born. All this purely mathematical development, that they were born from the stochastic limit of quantum theory, which we have developed mainly with Volovich and Arefeva in the Russian school, Kozyrev, Page, and many other, Teretyenko, many other in the Russian school, and many other not in the Russian school. But I will not have time to discuss. What I want to say is that everything was born, all this mathematical development were born from the concrete physical problem that we had to solve in the stochastic limit. And finally, but not less important, a thing which was, when I began to study this, I was fond of the foundations of quantum theory since I was a student in the university. But since then, foundations of quantum theory has taken a big impetus where it is related to the main topic of this talk. It has taken a big impetus because now we know that the quantum formalism will canonically arise in any classical probabilistic theory. But classical probabilistic theory in modern science is ubiquitous, from medicine to economy, to sociology, to linguistics, everywhere, to artificial intelligence, everywhere there is classical probability. So the foundation theory is now trying to develop this new intuition. How we develop the quantum intuition for classical random variable. And we know this is true for all. Okay, so now I finished my list. In the list, I mentioned the quantum Markov chain. Let me mention two recent developments in the quantum Markov chain direction that have been obtained. One is hidden Markov processes. Hidden Markov processes are essentially, in classical probability, can be characterized as functions of Markov processes. And as function of Markov processes. Now, the problem was, can we have, like we have since 1974, we know an analog of classical Markov chains, which are the quantum Markov chains. Can we know an analog of the hidden Markov processes? And this was recently constructed in a series of papers by Abdesattar-Soussi, Suedi El-Geteb, and myself. Two papers essentially. One has to do with the classical, and the other one with which has to do with quantum. They both appeared in the EDAQP journal. But some recent progress has been in the direction of application. In the direction of applications, I want to mention this paper by Abdesattar-Soussi and Abdesattar-Baroumi, which is Causal Architecture in Hidden Quantum Markov Process. In the hidden Markov processes, you have essentially two processes. One which is called the hidden process, and another one which is called the output process, and which is the observable process. And in quantum Markov chain, in the generalization that we did with Abdesattar-Soussi, El-Geteb, and Lu, I think also was in, and Jung-Ang Lu, in the EDAQP papers, we made a particular choice in our construction of hidden Markov processes. And Baroumi and Soussi observed that you can have a different choice, which also gives rise to a very interesting class of quantum Markov processes. But this class is not the hidden Markov processes that we had built. Okay? In some sense, they explain it is the same philosophy, but the hidden process and the observable process mathematically exchange their role in the formulas. And so you have a different process because you have a different conditioning. You always condition on the hidden process, which you don't know. So just a moment. Another application is in a preprint, in a paper by Abdesattar-Soussi, Suedi El-Geteb, and myself, in which we, using the theory of quantum hidden Markov processes, we have proposed a quantum generalization of the Viterbi algorithm. Viterbi algorithm plays a very, very important role. It was born essentially in the study of chips of solid-state physics, applications for computer, but it has found applications essentially everywhere in applied statistics. So it is a really important algorithm. It is related to control theory because also in this case, you reduce the mathematical problem to an optimization. Only that what you optimize here typically are conditional probabilities and not general cost functions. Okay. So now with this I have finished the list. Okay, this in this preprint, the main result is that if we use the quantum Viterbi algorithm, but we use it for classical probability, that is restricted to diagonal algebras, we obtain an improvement with respect to the classical Viterbi algorithm. That is, we obtain better results, higher approximation of the cost function. Okay. So with this, I have finished the list that I have. Now, I want to say to the organizer, well, but maybe before I finish my talk, I just want to mention what I promised, which is the Gaussian, to just give the idea. This is momentum. It's very interesting. This is the Hilbert transform, momentum, representation of momentum. But I think that the other thing can be quickly explained, because the main idea again is conceptual. To realize it and to find the explicit formula, I can assure you, takes a lot of work. But conceptually, the idea is very simple. Let me try to explain this. What do we mean by Gaussianization? This term was introduced in the first paper. Well, it depends what you mean by probabilistic quantization. Really, the first paper is is a survey that we did with Lu and Volovich on the notion of interacting for space. 2 years after, we discovered with Marek Bodzejko the bridge between one mode interacting Fock space and orthogonal polynomial. And this bridge, we considered only the case that I discussed today with you, namely one-dimensional, 1 degree of freedom, one random variable real valued. This is what we did in the paper with Bodzejko. But in that case, we proved that there is essentially an identity of category. The theory of orthogonal polynomial in one variable is equivalent to interacting Fock space in 1 degree of freedom, which we call one mode interacting Fock space. So for this, I want to describe this idea. What does it mean, Gaussianization? Gaussianization, well, first of all, why the name Gaussianization? You know that there are many characterizations of the Gaussian standard random variable, but one of the most famous characterization is combinatorics, and it says that you can have all the moments of a Gaussian random variable are uniquely determined by its covariance. Okay, so this is what I will adopt. This is the definition of Gaussianity that we will generalize in quantum probability. Now, why we call Gaussianization? We call Gaussianization because of the following theorem. Every classical random variable, the classical moments of every classical random variable can be expressed uniquely, not in terms of the classical variance, otherwise we have the characterization of Gaussian, but in terms of the quantum variance. This is true for symmetric variable. That is also true in non-symmetric, but we have to do a longer discussion. We have to, essentially the jumps create, as you know very well, additional difficulties. But the formula is essentially very similar. Formula is very, very similar. But the explanation, the conceptual explanation, is much simpler when there are no jumps. So when you have symmetric random variable. What is the explanation? Let me explain this. You have a symmetric random variable. So A0, remember the characterization, a random variable is symmetric if and only if the preservation operator is 0. Now, what does it mean? That this was already remarked in the original paper of Bodzejko and myself. Since X has a quantum decomposition, the classical moments of X will be expressed in terms of products of A and A daga. So let us call this the quantum moments. Okay. And we see that the quantum moments now, and with Wozeiko, we gave the first explicit combinatorial formula for this. And we included the non-symmetric case. So in the formula with Wozeiko, now we have a more powerful formula because we have, this is a recent result, we have the explicit formula, the recent result with Lu, and now we have generalized with result in a paper which is not yet published with Dauda Dico. And it gives the expression, you see here in the formula with Wozeiko, we had the sum here. But we have the formula, explicit formula for the single quantum moments. So this formula will be a corollary of the generalized formula with Lu in the symmetric case and with Dico including the non-symmetric. But what has this to do with Gaussianization? Let me try to explain. So this is my definition of quantum moment. So remember, the motivation is that if you take the classical moment, it will be a sum of quantum expectation value. This quantum expectation value we call the quantum moment. And this is the definition of quantum moment. Now, let us notice that I number starting from the vacuum on. So from right to left. Usually one, like here, for example, one does left to right, but this is simply a convenience operation. So let me try to explain what is the idea. Look at this expression. This is the quantum moment. One thing is obvious. This epsilon, since the random variable is symmetric, can only be creator or annihilator. But by default property, if it is an annihilator, this is zero. So see, if we exclude the trivial moments, we call trivial a moment which is identically zero, we must have that epsilon 1 is plus. So it's a creator. We have a creator as epsilon 1 is plus, means A epsilon 1 is a creator, is the creator, because we are in 1 degree of freedom. Now, if epsilon 1 is plus, there will be, if they are all plus, the moment is trivial, because it's zero, because F is epsilon 2, P, the last one is zero. You prove that for a symmetric random variable, if n is not an even number, the moment is zero by definition. It will be identically zero. This is true also for quantum moments. So n must be an even number, and we write n equal to p here. So if epsilon to p is annihilator, it will act taking a joint on the vacuum and gives again a trivial zero. So epsilon 1 must be minus, and the epsilon 2p, the highest, must be plus. Given this, since there is a change of sign, there is a minimum index where this change of sign appears. Let us call L1 this minimum index, okay? And then we define LP by induction. Let us examine L1. So what is L1? Or in general, LP. Put a P equal to 1 to be simple. So L1 is the smallest index in which the sign is switched from plus to minus. So instead of writing a minus, I write simply A, like in physics notation. Okay, so I write A instead of a minus. So since L1 is the first where there is the switch from plus to minus, we have this consecutive pair, which is A plus A daga. But if you remember, A plus A daga was omega lambda, because it's a gradation preserving. So in 1 degree of freedom, it must be a function of the number operator. And we know this function is omega lambda plus 1. Omega lambda plus 1 means that, however, this omega lambda plus 1 will act from a creator because here it is plus. So the creator begins from LP minus 2. And so it will give L1 minus 1. And now you iterate. This is done for arbitrary P. So the main idea is this. So you see, what is what in the Gaussian case, you have only one. The commutator, what we use is constant. Remember, the commutator is constant in Heisenberg relation. So this omega L is always 1. So the variance. And we find the standard Gaussian formula. But if the probability measure is arbitrary, you will have a certain element of the principal Jacobi sequence. So when you do iteratively, either you find 0 because you find a configuration which is identically 0, the quantum moment, or what you will find, every step, now you iterate, so every step will give you an omega. So the step, at the end, will have a product of omega. So the explicit formula of the quantum moment is a product of omega. And the delicate point is how to identify the indices of this product. Okay, so now what I want to do is I would like to leave some time for some questions, unless you prefer me to deal with one of the arguments which I mentioned and I don't dealt with. So I don't know what to do. I think if there are questions, we dedicate this last, say, about, not so much, few minutes.
Thank you very much, Prof. Luigi, for this nice presentation. It's really inspiring. And actually, I want to start with the very first question, going back to the old time where you were a student, like in Russia. And the first question is whether quantum probability is a Kolmogorovian probability or not. The second question, whether there is an anecdote that you can say that happens to you with Kolmogorov by that time.
Oh, well, is for that my period of PhD in Russia, 4 years were one of the best period in my life, and when I began to work I began to work in quantum probability essentially because Gelfand said, who was the person who gave me a lot of suggestions. I went to the Soviet Union just to know him and to work, if possible, with him. And he was so kind and very, very friendly, and he followed me very much. He gave me a list of books to read. I have still now this list, but I must confess that after 50 years, I have not yet read everything that he suggested me to read. But in any case, I kept as a treasure this list. And one of the suggestions he gave to me was inspired by the situation that was in the 70s. This was in the early 70s. And namely, he said to me, you must study stochastic process, operator algebras, and quantum mechanics. Classical probability essentially was essentially what we call now quantum probability is essentially a synthesis of these three things. But all the three play a very important role. And concerning Kolmogorov, he was in the 70s. I'm speaking of the very early 70s. The end of 1970 to summer of 1974. Kolmogorov was rather old already, so he was not giving talks, but occasionally he participated to conferences and or to official occasions in the um, in the in the Moscow University, where he had taught all his life. And my great luck was one of these occasions, very rare occasions, in which Kolmogorov, from his house, that is out, still now conserved by the curator, is Albert Shiryaev, and is outside of Moscow. So to come to Moscow for him was a real journey. And for this, he one of these occasions in which he came to Moscow was my the defense of of a series of dissertation, among which of candidate nauk dissertation. This is PhD, Russian PhD, and my defense of PhD, Russian PhD candidate nauk was that. And the fundamental new point of my thesis was the quantum Markov chains. And I realized it. At that time, I didn't know notions like complete positivity, like completely positive semigroup, and so on. But I realized that the quantum equation that I found from the my non-commutative Markov processes was a generalization of Schrödinger equation. And so I mentioned it in the defense because still it seems to me very curious. Now we know very well this is a standard form of quantum Markov processes, that the process canonically associated to a quantum Markov process is a Markov semigroup. At that time, all these things were not known. And so I mentioned this. So after my thesis, I sat near the blackboard, and Kolmogorov came with and sat near to me and said to explain better what I mean by at that time I didn't call, they were not known, obviously. The GKSL generator came 2 years later. And so I called the quantum Chapman-Kolmogorov equation. And so he said, but what is this quantum Chapman-Kolmogorov equation? He heard this name, and he was very curious. And then the converse question appeared many years later, because I met Kolmogorov, now not in an official equation, it was a conference, but it was a party in the house of Vitas Statuliavicius, who was the main organizer of the famous Vilnius conference, which was the heir of the Berkeley Statistics and Probability Conference. And there I met Kolmogorov in this party, and I asked him, Andrei Nikolaevich, you are one of the greatest mathematics of all epochs, and you have contributed to all branches of mathematics, many branches of physics, of linguistics, of every kind. But how it happens that you were never interested in quantum theory, which is a probabilistic theory? And he thought one moment, and then he told me, it is not true that I did not think to this. In fact, I thought about this, but I never found anything interesting to say. And then I understood, because if you know what Kolmogorov writes at the paper, what he wrote, for him to say something interesting and to publish means to revolutionize the subject. So what he was saying to me, I didn't find any important new point, because Kolmogorov was a classical mathematician. Only if you really think carefully, his contribution with the classical analysis. Quantum theory was a word and at that time, even mathematically, it was not. Remember, we were speaking he was already very old in the 70s. So when he was very, very active, the mathematical description of quantum theory were very, very poor. They mainly physicists were doing that. So you see, Kolmogorov also thought of quantum probability. But I hope that my talk will show you that the quantum probability nowadays, after 50 years, has a very wide range, and can be of inspiration for many types of different mathematicians.
Thank you very
So I
much.
don't know
It's
if
really
there
inspiring.
are other questions.
Now,
Can I
if there are other questions, colleagues, please just open the mic and ask. If there are.
Yes, can I ask a question? Can you hear me?
Yes, you have to speak a little bit louder.
Okay. Thank you
Yes.
very much, Luigi, for the very nice and deep talk. I have two questions. The first one, in foundations of quantum mechanics, complex numbers are very important. We have to understand why they are introduced. You consider classical probability and real valued random variables. Now, orthogonal polynomials are also real. Why you admit complex numbers?
Right, complex numbers. This I have a very mathematical answer. This is in the last part that the last issue that I didn't discuss. You see,
How to
this
justify
the foundation of this is foundation, debate of foundation. So the answer to the question is complex numbers are written in the transition probabilities. That is, if you have the transition probabilities that are given in a paper in 1982 with Fedullo, I proved the following theorem. If you take the classical spin, single spin, pay attention, not single spin variable. If you take the classical spin 1/2 transition probabilities, so they are 2 by 2 bistochastic matrices, and you ask if you have 3 different directions of spin, and you ask yourself, does there exist a Kolmogorov model for these transition probabilities? The answer is not always. So there are experimental data of quantum physics that oblige us to go beyond the Kolmogorov model. Let us take the Hilbert space model of quantum theory. Again, by construction, all the spin variable, the triples of spin variable can be described by Hilbert space. But inside this quantum triple of a spin variable, there exists a huge amount, inside the majority of them, will not allow a Kolmogorov description.
No, this is, I understand.
Moreover, you ask,
I'm sorry.
among this triple of spin observable, which one admit a real Hilbert space? And you see that they are measure 0. It is a geometric interpretation. So the complex numbers are written in the experimentally measurable transition probabilities.
Yes, this is, I understand, thank you. But my question is, why complex numbers are natural in your approach?
You mean, why do they arise in classical probability? Well, there is an uncountable number of theorems of classical probability which are proved using the complex Hilbert space. One of the reasons is, for example, because this allows to make use of a spectral theorem, which is much easier in the complex than in the real case. So there are many. The use of L2 of complex numbers and not L2 of real numbers in classical probability is enormously widespread. Is not introduced by me or by quantum probability. Long before we have important theorems and results of classical probability. Okay. There is a whole branch of classical probability which deals with complex random variables. Okay. You see?
Thank you. The second question is, in your approach, what you can say about the measurement problem?
Measurement problem is to do
From your point of view.
what is not a measurement problem, is to do with what is in fact the very essence, not of what I discussed, but of the second topic I mentioned, quantum conditioning. For Neumann measurement formula, we can interpret as the first mathematical example of quantum conditioning. But there is a huge amount of discussions that we can do from the mathematical counterpart of we can say that quantum conditioning is from the mathematical point of view, the quantum theory of measurement. The mathematical aspect of the quantum theory of measurement. Of course, there are fundamental physical aspects, but the mathematical aspects of the quantum theory of measurements is quantum conditioning.
Okay. Thank you very much. It is a very deep and nice approach.
Thank you for that question. Yes.
I have a question, please, Dr. Ansattar. Thank you, Professor Luigi, for this nice talk. I have a general question. What are the potential real-world applications of probabilistic quantization in science and technology?
That is a very good question. That is a very good question. And you see, the theory, as I said, it was born from the stochastic limit of quantum theory, so from problems, concrete problems in physics. Now we are understanding that for classical, there are, how to say, I would not say at the moment we have several small things, but we have not what you might say the killing application outside physics.
Okay.
Not yet.
Okay.
I'm sure it will come, but it requires time. Because you see, classical probabilists are not used. Quantum probability, in some sense, is in the middle of functional analysis, classical probability, operator theory, and now also of statistics. For example, what I mentioned before, the fact that there are non-Kolmogorovian statistical data. Well, it's obvious that such non-Kolmogorovian statistical data do not exist only in physics. They should exist, they must exist in medicine. And, for example, with my friend Andrei Krenikov, who has been the pioneer of this line of research. That is, let us look for non-Kolmogorovian data outside physics. I mentioned it with the three-spin example. Once you have the experimental probabilities, which you measure, typically they can be correlations, they can be joint probabilities, they can be conditional. Typically in quantum theory, they are conditional probabilities. So they are experimental data. And you need the mathematics of quantum probability to answer the following question. Do these experimental data admit a Kolmogorov model or not? So the most important application now are going in this direction. Are there natural sources of data which are non-Kolmogorovian? In a paper with Krenikov, myself, and Masanori Oya, we took the data of 2 Nobel Prizes in economy, Tversky and Shafir, and they had shown that their data could not be described by a classical Markov chain. What we proved is that they cannot be described by any Kolmogorov model. But we constructed a quantum Markov chain model which could describe this model.
Okay.
So that is, to my knowledge, the first example of some data which come from outside the physics, in that case, we took from Tversky and Sapir, which are economists Nobel Prize. And we proved that they are non-Kolmogorovian. But we proved that we can use the quantum. But now, with the talk that I did today, there will be cases in which they are neither Kolmogorovian nor quantum. But we can use this probabilistic quantization.
Okay.
You see? So this is one direction. But there are many others. For example, Abdesatar Soussi working very hard in application to machine learning and other applications. And I think many other people are working on many different applications that simply I don't know.
Okay, thank you. Thank you for this answer.
Dr. Rafiq?
Yes.
I have a question.
Yes, Dr.
Yes, thank you very much, my Professor Luigi, for this talk. I think from this talk, we see that there is a vast number of questions which await solution. And maybe this requires significant effort and collaboration across various disciplines within mathematics and maybe other diverse applications. And then I join the comment by Professor Rafiq. It will be, in my point of view, highly beneficial to collaborate with research working on quantum computing, in quantum control, and so on. Because maybe the main question about the theory from people outside mathematics or outside research in this line is concrete application of this theory. And now one can see that there is many attempts in the novel technology to use concretely this theory, even in very simple cases, using spins and using this kind of commutation relation. Last week, I discussed with young people working in quantum control. And then I am surprised that they use quantum Markov chain now in some quantum algorithm instead of the classical Markov chain, really now, as for a concrete application in University of Stuttgart in Germany. And then I think after a long discussion with Dr. Suisi about this possible application of quantum Markov chain in machine learning, if we can go successfully to concretization or concrete collaboration with people working in this area, this can contribute a lot for our research line. Now, if I wanted to give a concrete question, maybe related to the content of the talk, in the point concerning the possible extension of probabilistic quantization to multi-dimensional case. It seems that the main constraint is the possible fully generalization of Favart theorem in quantum setting. And then I'm not sure if after our paper with Dahri for this question, if there is some recent research which can give a fully general formulation of Favart theorem, which open the door to use more this quantization for general quantum Markov process.
Yes, there is. There is a paper with of Abdallah Dari and myself. We did this generalization to infinite dimension, and this includes boson, all the boson quantum fields that are used in physics. But we have now the biggest problem. Now we want to have, and this is what I mentioned, this open problem. We want to have a concrete, linear, non-linear example of probability measure in this direction. And these concrete examples are known at the moment only in finite dimension, and they are due to Aurel-Stan.
So
At the moment, there is not a really nonlinear example in infinite dimensions. But in finite dimension, Stan was able to do this.
Okay. So I should see maybe this paper, even if it is in the finite dimensional case.
Finite dimensional case, is very hard because it's nonlinearity. Nonlinearity, even in the quadratic case, is hard.
Second comment is about the quantum conditioning. Quantum conditioning is also a big issue coming from people working in classical probability. So I really didn't got your comment about this point, and you say that this can be seen or tackled from quantum independence
which comment? The comment on Gaussianization or the comment on the fact that what in the literature are called stochastic independencies are in fact dependencies, algebraic dependencies, simple algebraic dependencies.
And this is realized as a final result. No question about this, about the type of independence.
Well, with Lou, we have done this in the case of Fermi, but in the same paper where we did the Fermi, we discussed it because you see, when you have the Bose-Einstein, a statistic correspond boson quantization, and you have so-called Bose-Einstein statistics. When you have Fermi, you have Fermi-Dirac statistics. And so we said, okay, since now we understand that all the known dependencies are algebraic constraints on classical random variables, what will be, for example, the analog of Bose-Einstein for free probability, for monotone, and for other possible probability? There are uncountably many, as we proved with Bose-Echo, uncountably many notions of independence. In fact, with Bose-Echo, we have the following theorem. Given any probability measured on the real line with all moments, then there exists a notion of stochastic independence such that this arbitrary probability measure is the Gaussian for that notion of independence.
Oh, okay.
You see?
Okay, Professor, I got it. Thank you very much.
Thank you for the question.
Professor Accardi.
Hello, Iskander. Nice to see you.
How are you?
Fine,
it's
very well.
To see you here with my colleague in Arab Saudi.
What?
It is a pleasure to see you here.
Yeah, also for me. I saw you, and really this talk, I am very grateful to the organizer. It gave me the possibility to see so many of you. That for me is a joy, a real joy.
So I have one comment about the algebra approach from classical to quantum, and there is another analytic approach with Hilbert space for square integrable function and the multiplicative operator. So the advantage of analytic approach is you can say the extension to, for example, finite quantum. So what is the advantage of approach, algebra approach from classical to quantum?
Well, the great advantage is that we have now discovered that every classical random variable has a finer structure. Now, in the case of physics, they discovered this for a very special random variable, Gaussian. And they were able to extract enormously successful information on natural phenomena. So what we want to do is, let us do what the physicists have done in these 100 years to use the Gaussian quantization to extract information on a special probabilistic physical phenomena. Let us use probabilistic quantization to extract finer and deep information in all fields in which probability is applied. And probability is applied in almost all fields of science. So that is what we want to do with this quantum probabilistic quantization.
Okay, thank you.
Thank you. We have Dr. Diku. Dr. Diku, you have a question?
Yes, thank you so much. Can you hear me?
Yes, we can hear you.
Okay, I want to appreciate Professor Accardi for the very beautiful exposure into this class of research. I have a number of questions. The first one is we want to know, is there a quantum Heisenberg-Lie algebra? That's the first question.
Of course, there are. We have studied the complexity index. The complexity index that we studied was born exactly from this problem. What is the structure of the Lie algebra of a classical random variable? But this is a completely new class of infinite dimensional Lie algebras that nobody studied up to now. They are very interesting. Some are for the simplest measure, like arcsine or semicircle, which have trivial Jacobi coefficients, are not known. But if you take the very simple case, the Jacobi coefficients of the powers of the Gaussian, nobody knows this structure of these algebras. They are very interesting, and their structure is strongly related with a long series of papers that we did with Andreas Bukas, which is the renormalization, what we call renormalization of a commutation relation. But here we have the Lie algebra. In that case, we had the Lie algebra, but we have no representations. We were not able to find representation. Here we have a representation, a Hilbert space. So they are special Lie algebra realized on Hilbert spaces. They're very interesting for Lie algebra specialists. I think this will be a field that those who really have the courage to enter, it will be difficult because they are infinite dimensional Lie algebra. But those who will have the courage to enter will have very good results.
Thank you, Prof. Professor Igwe is working on something like that. He would interact with you about
I hope. Yes. This is very interesting.
Yeah. The second question. The second question basically is about the measure that is being used is the Gaussian measure. I mean, all true, and which leads to the boson cases. I want to know, for the fermion case, are there results existing?
Yeah, Bernoulli. Fermi is Bernoulli. But with the coupling. The coupling is in the case, the algebraic constraint. I am speaking of this algebraic constraints. I say what we call quantum independence are algebraic constraints. The first example of algebraic constraint was Heisenberg, was the Pauli exclusion principle. Applied to Bernoulli, this is our paper with Lou. Applied to Bernoulli, this gives, and together with the Pauli exclusion principle, you deduce the Fermi anti-commutation relation. That is the result with Lou.
Okay. Okay, thank you. Then the third question is about the quantum conditioning. Yeah, I know that in this presentation, it was not quite explicit. I want to request that I'd love to see where the quantum conditioning is being used or applied. So that it was when the question about measurement came up, that, okay, one can now see or know that measurement is embedded in the quantum conditioning. I don't know if there is a paper where you use the quantum condition. I would love to see it.
Well,
Thank you very much.
quantum condition is enormously used. For example, because you see, typically people looks at the dual picture. The dual picture of conditioning is a lifting. So conditioning means from an algebra to a subalgebra. Lifting means you have a state on a subalgebra and you want to extend to a state on a larger algebra. So this is the dual picture of conditioning. And we wrote a paper with Oya about lifting. And there are a lot of, all quantum Markov chains are based on lifting because it's iterated lifting on larger and larger algebras. Okay, so there are a lot of applications of condition. You must understand very well this point, that lifting and conditioning are dual operations.
Thank you so much, Prof, for the talk. I think we all enjoyed it. Professor Bassi is also here, and he also appreciates the talk. Thank you very much. Thank you. Yes.
Thank you for the
Prof.
nice
Sattar.
Thank you very much.
Prof. Sattar, I have some question.
Yes, please.
I would like,
Yes,
firstly, I would like to thank Professor Accardi for this values talk. It is very important to see Professor Accardi. I have two technical questions. So my first question, it is about, it is possible to find explicitly the expression of quantum momentum in the non-symmetric case. This is my first question.
No, in the non-symmetric, this is a subtle point which has to do with complexification. So in the non-symmetric random variable have not a natural quantum momentum. You can invent some observable, but you see, our philosophy is to deduce, not to put things by hands. Because the fundamental objects in mathematics are, of course, you can invent a definition. You can invent many definitions. But or another possibility, not artificial, could be the following. There are many characterizations, for example, of momentum. And for example, one characterization was used by Stan. He introduced momentum using another characterization of momentum, a purely quantum characterization of momentum. So there could be different characterization of momentum that admit generalization to the non-symmetric case. But I don't think that in the non-symmetric case, this is a subtle point, because when you do you want to have the complexification. If you want that to complexificate the creator, if you want that the creator map is a complex random variable, is a complex linear, not only real linear, then momentum cannot admit. Non-symmetric observable cannot admit momentum. Yes, but in physics, creation map is complex linear. So we were inspired by this. You can drop this assumption, but I don't think you have a natural condition for non-symmetric case.
So my second question is technical. For example, the paper of Q Azai and Kibo, if you have a classical random variable with element, we can find the orthogonality of polynomial via the generating function in condition of the expectation of product of two generating function is a function and S a product of S of NT. There is some measure, for example, if you on the classical probability, but the expectation of the product, we don't obtain a function of s time t, but we obtain, for example, a family of polynomial with each called apple polynomial, and we have a paper with you in this direction about apple polynomial. So my question is, if we don't have orthogonal polynomial, for example, we have a family of apple polynomial, can you find a result about the quantum decomposition in this direction, for example?
Frankly speaking, I have not thought about this. So I cannot give you an answer because I did not thought about this problem. It is not excluded, but the quantum decomposition in the approach now of probabilistic quantization is extremely related to to one generalization of three-diagonal relation.
Yes, but in the case of we don't have an orthogonal a family of orthogonal polynomial, we don't have creation and annihilation, and this
Right. That's the point. So,
my question is, there is another method to find this quantum decomposition for any random variable.
I would be very happy. I would be very happy to have such a result. However, I don't at the moment. I can only tell you that such a result at the moment is not in the literature. But of course, if somebody will be able to do that, it will be. I will consider personally a great success.
So my question is, it is possible to find this quantum decomposition? This is my question.
My question is that I don't know. My answer is this.
I think
I don't
MC
know.
is
I cannot tell
technical.
you what I don't know.
Okay, thank you. Thank you.
Okay, great. So maybe we can have only one last question if anyone have a question.
Hello, Professor.
Okay.
Just I would like to thank you for this interesting talk, and which encourage us to continue research, especially in the machine learning using the hidden space. I'm think that there is some because I have some information on intelligence artificial, and we use the layer that we can in quantum theory use them in similar to in hidden space. Maybe in this direction we can collaborate with Arcetar Swissim, for example.
So I'm not sure I understood the question. What do you use
The hidden space, the different layer of hidden space, to use them in the machine learning or deep learning.
Yeah, this I am not personally working on this, but Abdesatar Barumi, Abdesatar Susu, they are working on this. You should, they can answer this question, but personally not, because I'm not working in this specific direction of machine learning.
Okay, thank you a lot, Professor, for this very interesting.
Thank
And
you for.
see you in Monastir next
I hope.
October.
I hope to see you there. Very good.
Yes.
Very
Okay.
good.
So thank you very much. I have just a last
Thank you.
question, though, because you mentioned the two approaches, the discrete one, which is quantum Markov chains, and you mentioned it's like extension of the Schrodinger equation. On the other hand, you have the continuous dynamics through the Limblad equation, which is also extension of the
Yeah,
Schrodinger.
what I found was what now they call quantum Markov semigroup. I did not find the generator, but the quantum Markov was clear to me.
Is there like a bridge or like between the two, a unified approach between the quantum Markov chains and the Limblad equation? You think
They are the same. They are the same, and there are many theorems that show the converse. This is called dilation theory. So, to create, you see, for example, Hudson-Partasarati theory can be interpreted as a dilation if you are interested in dilation. I am, you see, but they are very special. I want to warn you that in this case we are speaking not of general quantum Markov process, but of Markov process of a very special type, which I call random walk type Markov process. For them, the continuous version is fully developed. But for non-type, then the conditioning problem enters. And there you have troubles.
Thank you very much. It's like exactly 2 hours.
Okay. So
thank you.
we can
Thank you.
finish.
Thank you for your time.
If, of course, if there are no other questions.
If there are no other questions. Okay, thank you very much, Prof, once again.
So thank you. And I think we go.